we talk about flux. Just now was turbulence. And turbulence is related to flux. Now we're going deeper and deeper into eddy covariance technique. And why eddy covariance is important? Because you'll be able to measure flux directly. So flux is directional. Flux means the rate of transfer of a quantity across a unit area. So basically like that. So how much of that quantity moves through a certain area. And it could move up or down, or it could move left or right. So the net flux can be split into components in the x, y, and z directions, just like u, v, and w. If a greater flux enters a volume than leaves, then there must be a net increase of that quantity within the volume. For example, this is the volume, and if the flux going into this volume is much larger than the flux going out, then logically, it should be an accumulation of that quantity in that volume. Does that make sense? Just like mass balance, right? So we can guess the accumulation inside by knowing the flux in and flux out. The minus of this and this will give us how much is accumulated inside. That's flux. Now we go to covariance. Now covariance is actually flux. Okay? But we haven't connected the two yet. So covariance in the atmosphere, fluctuations in velocity are often accompanied by fluctuations in scalar values such as temperature, humidity, concentration. Oh, there. I wasn't looking at it. So, for example, in a field of thermals, there are regions where warm air is rising, positive potential temperature, theta prime, accompanies positive vertical W, W prime, surrounded by regions where cold air is sinking, negative W prime, accompanies negative theta prime. One measure of the amount that theta and W vary together is covariance. For sigma U, you calculated just now. That was variance. But covariance, what does that mean? Covariance is a variance of one component multiply a variance of another component. And this is how we measure flux. Okay, you measure sigma U just now. For sigma W, you have sigma W. And then we measure temperature, sigma T. So the variance of this multiply the variance of temperature gives us the covariance. So this quantity, this combination of two quantities gives us the flux. So that's what it means by here. If warm air is rising, going up, positive potential temperature, that means this sigma prime, theta prime is positive. That means it's higher than the average. And the vertical velocity is positive, W prime, higher than the average. That means it's upward moving air plus outward temperature. So this is a positive flux. A negative flux is you have W going down and temperature also negative. So that is a cold air sinking. So we call that as, so this is cold air sinking. This is positive air rising. So for us to get this flux of heat, upwards or downwards, of course we need, right? And we also need these two, both you measure at 10 Hertz or above. So notice, okay, there's an average here. There's an average here. So at this point here, W corresponds to this point here. So this one minus this one minus this one, that value times this value. And then you do for every point. Do for every point. And then we get the average. For half an hour, that is the flux for that half hour. That's called covariance. Because this is one variance, this is another variance, this entire thing is the covariance. So that's what it is, basically. So if warm air parcels are rising and cold parcels are sinking, as in a thermally direct circulation, then W prime theta prime is more than 0. Covariances can also be negative or 0 because it's direction, depending on the direction, for different situations in the atmosphere. Now, variance represents kinetic energy associated with motions on the scale of turbulence. Similarly, the covariance is a measure of flux due to this motion, such as the vertical heat flux. And this is transport of moisture, transport of heat, transport of pollution in the atmosphere that we talked about in the previous slide. So here, it's about the same thing as what we discussed just now. So covariances can be interpreted as fluxes using the following concepts. Consider a portion of the atmosphere with a constant gradient of potential temperature as sketched in the right figures. So I think this one we have to go through slowly. There is a certain height. This is height. This is potential temperature. For one case, unstable. This is stable. This line here is for temperature. So this point moves up. This is W prime star. W prime positive. This is W prime negative, moving downwards. It's difficult to see. So let's say if the W prime is moving downwards, so W prime positive, and if this W prime is downwards negative, if moving upwards it's positive. So this one means that the W prime carries this temperature downwards. So down falling parcel of air, and this is rising parcel of air carried by the vertical component. That is for W, but what if it's for temperature? So this is hot temperature, this is cold temperature. Notice that this one is negative. So notice if it's moving negative, and this is negative, negative times negative, positive. Now this is positive, while this is positive as well. Positive times positive, positive. So positive flux, negative flux. This is the other situation for stable. This two is positive, but this one is negative. Negative and positive becomes negative flux, and this is the opposite direction. So the idea here is to show that, okay, one deviation could be positive, the other could be positive. If it's both positive, it means upwards. If one is positive, one is negative, downwards. If both is negative, upwards. Because it consists of two parts. So consider an idealized eddy circulation consisting of an updraft portion that moves an air parcel from the bottom to the top of the layer, and a compensating downdraft that moves a different air parcel downwards. So air mass is conserved. Mass up equals to mass down. However, the air parcels carry with them small portions of the air from the starting points, and these portions preserve their potential temperature as they move, resulting in a flux as well. Now be shown. Let's see what's next. Yeah, this is the description of the previous slide. Just now we saw the slide, right? This is what they describe. Suppose that we erect a short mass instrumented with anemometers to measure the U and W components. We record the instantaneous wind speeds for every 6 seconds. This is not exactly 10 Hertz, but it's higher than 1 minute. For about a minute, resulting in the following 10 pairs of data. So you have U and W. Notice the values. You see the values here are larger. The values here are smaller. Because vertical winds are usually very not that large as the longitudinal wind. So find the mean, variance, and standard deviation of each variable. Also find the covariance between U and W. Okay, the difference here is that you did this just now for sigma U. But then you can also do this for sigma W. But now calculate the covariance. That means U and then W. And then you combine the two using because of that covariance, and you get that covariance of U and W. So the answer is here, if you'd like to try it out. Okay, aside from just now you were introduced to W prime, theta prime, right? This is the transport of heat, either up or down. How about transport of momentum? Have you heard of that? So far, you have. How can momentum be transported? What component do we use? It's W, U prime. Transport of humidity is W, Q prime. Transport of concentration is W, C prime. So this is mass transport, also mass transport, heat transport, momentum transport. So you can actually calculate momentum transport just by having an anemometer that can measure the three components, U, V, and W. So if you have that anemometer, it measures this thing. That is the momentum transport, the turbulence the transport due to the transport of friction, the transport of surface roughness. So let's read through the discussion here. So 1, the turbulent variations of W are more intense than those of U, even though the mean wind speed for W is 0 in this example. If you look at this, okay, this could be high in magnitude, but the turbulence is 1.2. For W, it's lower, but look at the turbulence, it's 1.4. This is square. This is without the square. Notice that the turbulence, the vertical turbulence is much higher. It's not much higher, but it's higher than the sigma U. Because there's a lot of variation for W compared to U. Now, U and W tend to vary in opposite directions on the average, as indicated by the negative values of the covariance.